So in this section, we're going to look at discrete random variables. What that means is for our random variables, it's things that can happen randomly, random outcomes. And what we're going to have are these discrete cases, meaning there's only a certain number of outcomes or certain types of outcomes, but then with each outcome, we have an associated probability. So we're going to see something called a probability distribution model. And that's what's showing up down here with this example we're going to look at, where we have a cafe observed the following distribution for number of cups of coffee sold in a day. So this is telling us is there's these discrete options for number of cups of coffee. They either sold 30 or 36 or 42 or 48 or 60. What we're seeing from this chart is that at no point did they have a day where they sold 41 cups of coffee. That never happened. They only had these 5 scenarios, which isn't very realistic, but it'll work for our example. Then what we have are associated probabilities. So it's saying that, yes, we sold 30 cups of coffee, but that only happened 10% of the time. Whereas we sold 42 cups of coffee, and that happened 30% of the time. So we have these possible outcomes. We also get these kind of weights to them. This is where weighted averages come through, in that we give a certain kind of probability or percent of the time to each of the different scenarios. So with that, how we calculate the mean and standard deviation here changes, because when we calculate the average and our standard deviation, we want to give more weight to the things that happen more often. So we'd want this 42 to hold a lot of weight. Same with this 36 is up there as well. But where this 30 occurs, we don't want that to overpower the calculation of the mean, because it only happens 10% of the time. So that's where when we have our expected value, which is the same thing as our mean and standard deviation, with calculating these, we're taking into account these possible values for our variable x, and then also their probabilities and how those work together. So what we're going to do through this section is calculate expected values and standard deviations. So first let's calculate expected value, where they're asking how many cups of coffee can they expect to sell on average. So you can use this different notation. It's a mean. It's also, you can use E of x for expected value of x, but this is our formula right here. So let me just use our mean notation. So let's see how we would apply this. So our x values, that's what's coming through up here. Those are our possible numbers for x. And then we have times their probabilities. And if you remember this symbol here, remember that sigma? That's our summation notation. And that's just telling us to add. So what we're going to do is take these x values times their probabilities and then add on, and then make sure we go to the next scenario. So for this one, where we have 30 with its probability of 0.1, we would take our x value of 30, multiply it by its probability of 0.1, and then to move on to our next scenario, we add. That's what the symbol tells us to do, put addition between them. And then we use our next x value times its probability, which is a 0.25. And then we add. And then we move on to our next x value times its probability, add on the next x value times its probability, add on the next x value times its probability, until you use up the entire probability distribution. Something to make sure that you know you do have a probability distribution, double check that your probabilities, this should be covering your sample space, meaning you should have everything contained. And to make sure you have everything contained, always double check adding up those probabilities. Because if we add up these probabilities, that should always equal 1. If we get over 100%, that means we covered too many scenarios. If we get out less than 100%, that means we don't have enough information there. But if we get out 1 exactly, it means, yes, these are all of the possibilities and all of their probabilities. So if we throw this into a calculator, we'll get out a 43.2. So that's how we calculate expected value. Take the x values times their probabilities. And notice, say we compare this to how we used to calculate means. I mean, how we'd calculate means if we didn't have these probabilities. So the old way of calculating a mean. So how we usually calculate a mean is you add up the values. It's like adding up those x values. And then we divide by how many of them there are, which we have 5 scenarios there. So if we do that, notice that we get out something, let's see, we plug this in. This isn't a great scenario because it actually comes out to be the same. Why it comes out to be the same is that there's this balance where here's our highest probability, there's a 0.35 added up on the left hand side, 0.35 on the right, so it balances to the same spot. But let's say for a moment, and this is how it will usually work, this is just kind of a weird scenario, this is usually different than the expected value we get out. And it's because with this calculation, it's treating them as equal weights. It's giving them an equal weight across the board, whereas here we're taking into account, actually that's making up 10% instead of this making up 1/5 here. This is kind of giving 1/5 to each of these values, whereas here it's redistributing those percentages. So sorry this kind of ended up being the same, but usually they'll be different. And it's because our old way gave equal weights, and now with this new way, we're getting these different percentages out. But as you can see, sometimes they end up being the same if you get this kind of nice balance going on. Let's talk about the formula for standard deviation. For standard deviation, we're going to end up with this addition. We're going to take each of our x values minus the mean, which is before, that whole idea of deviation is distance away from the mean. So we want to see how far each of these values are from our average, and then we square them because, as we did before, we don't want those negative values. So we take our squared deviations, and something that's missing with this formula right here is our square root. We need a square root over all of that. So that we undo the squaring that we're doing there, just like we did before with standard deviation. And then what we're going to do is apply the probabilities. Because again, if 30 has this certain deviation from 43.2, we need to take into account. So let's look at how this calculates down here if I wrote this out. So our standard deviation, we're going to have this big square root. So I'm just going to draw our big square root symbol. And then we're going to take our x value. So our first x value is going to be 30. Subtract the mean, square it, times its probability of 0.1. And then, once we take care of that for our first scenario, then we add. And we go to our second scenario. So 36 minus 43.2, square that, times 0.25, and then we add on and we go to the next scenario and the next until we get to the end where we're adding on 60 minus 43.2, squaring that times its probability of 0.15. So the theme that you want to see across these, so you have your big square root symbol, and then what I think of is each of these is starting with our x values. So these values we can see coming from our table. Then you're always going to have subtraction, and then this number should be the same in each of the terms. Because 43.2 is just the mean, that's not. Don't forget those square symbols, and then you'll have the second row of our table coming through with the probabilities here. But if you think of these additions as a separator, you can kind of see this form coming through within each of those sections. Then we just want to throw that into a calculator all at once, and that's going to give us an 8.82. So what that tells us is we expect to sell 43.2 cups of coffee in a day. And on average, that deviates by 8.82 cups. So we get our mean and our standard deviation.